Okay, now that we've done some hypothesis testing on the difference between two proportions, we need to do confidence intervals. And basically the idea is if we find that our null hypothesis was actually incorrect, in other words, if we find that the two proportions were not necessarily identical, then the natural follow-up question is, well, then where is that actual difference between proportions? And that's what the confidence interval is designed to answer for you. So let's take a look at the new problem from the exact same data. So confidence intervals between proportions. The question I want to answer is this. Is the proportion of married mothers who are smokers different than the proportion of non-married mothers who are smokers? So what I want you to do is in a moment, put me on pause, go to your Google Sheet and actually build out the entire hypothesis test. I have all the answers here, but this is literally a picture. Oops, that's not what was supposed to happen. There we go. This is literally just a picture. I'm not going to click on it and show you how I got any of these. So you need to go build the hypothesis test for this question, which means you need to build the appropriate pivot table. Then you need to get all of the proportions. Then you need to get the difference, the pooled proportion, the standard error, the p-value, and then verify that my conclusion makes sense to you. Now, one thing to note is that I'm doing a two-tailed test here because I'm truly just asking, are they different? So when you get one tail on the hypothesis test, make sure you double it so that it actually gives you both. So in other words, if you get 0.00035 something, then you probably just need to double this and you'll be fine. Okay, put me on pause, go get this. Yeah, I'm actually serious, go do it. You're gonna need this here in a second. Okay, good. All right, you're back. So, when we build a hypothesis test, when we build a confidence interval, we have taken the original hypothesis that we built everything else on and threw it out the window. We know that the proportions are not equal to each other. So we need a different formula for our standard error. Our pooled standard error is no longer going to do the job because the pooling process assumed that the two proportions were equal. But now we're just admitting to ourselves that they are likely not equal to each other. So I have a new standard error formula, which I'll walk you through in a second. And then the confidence interval is really the same as what we've done in the past. You take the statistic that you had, in this case it's the difference between two proportions, plus or minus some critical z-score times the standard error. So let's go build this dude. I'm going to do this the same way I've done in the past. I'm going to try and put these side by side. Hopefully we can see everything. Okay, so here's all the stuff that I had on the previous slide. You should be able to build all of this. Again, if you haven't, you need to. And I'm going to slide it up a little bit because I don't need to see anything but those statistics at this point. Really, it's just this information that I need. Okay, so this guy right here is P1 hat. And this guy right here is P2 hat. The little hats that I have on there say, hey, I'm actually measuring something from the sample, not the null hypotheses. Okay, so my standard error for my confidence interval is, if you just cover up one piece of this, this should look like the standard error formula from one proportion. And that should look like the standard error formula from one proportion. We're just putting those together. So square root of P1 hat times parentheses 1 minus P1 hat divide by sample size. Don't end your last parenthesis there, plus, now I'm going to do it again, P2 hat times parentheses 1 minus P2 hat divide by sample size. Now I'm going to end the square root. Okay, so I get a standard error formula that's not based on the assumption that the two proportions are equal. Okay, there's my standard error formula. Now, if we're going to do a confidence interval, we need to have a confidence level. And let's just say that I'm 95% confident here, which means I've got 2.5% on either tail. And so my critical z-score is norm.s.inverse of 0.975. Remember, the 95% plus the 2.5% in the tail, which is about 2. Okay. So my margin of error, which is my critical z-score, equals my critical z-score times my standard error. Same way that we've done this before. This guy right here is called the margin of error. And really remember, the margin of error is just how much wiggle room you're allowing yourself on the difference between proportions. So now I get a lower estimate and an upper estimate. My lower estimate is my difference in proportions. That's this guy. That's the difference between P1 hat and P2 hat minus my margin of error. My upper estimate is my difference in proportions plus my margin of error. Okay, so our conclusion now is that we are 95% confident that the true difference in proportions between married smokers and non-married smokers is between 2.8% and 11.7%. Now, the other way to read this is that there's between 2.8% more and 11.7% more smokers who are married versus non-married. Right? And our proportions are saying, well, the difference was actually 7%, and we're saying it's, well, between about 3 and 11. Right? Because remember, with a confidence interval, you never just want to say one answer because that's absurd. You know it's really not that one answer. You know that it's not just 7.3%. It's between something a little less than 7% and something a little more than 7%. And that's the sort of thing that a confidence interval does for you. So if you need to, go ahead and rewatch this video, and then we're going to build one more confidence interval.